Hello and welcome to m253 here at Cañada College. My name is Lapuz. In this video, we will be doing checkpoints 5.33, 5.34, and 5.35 from section 5.6 in our textbook. So our problem is asking us to consider a triangular lamina with vertices at 0, 0, 0, 3, and 3, 0. And then they want us to look at a density function, rho of xy is equal to the square root of xy. And then in checkpoint 5.33, they want us to find the mass. In checkpoint 5.34, they want us to find the moments, mx and my. And in checkpoint 5.35, they want us to find the center of mass. So on the side here are the formulas that will be needed. The mass of the lamina will be a double integral over the domain D, or in this case R, of the density function as a function of x and y, and then we're going to integrate that with respect to x and y in whatever particular order we want. Mx and my are going to be similar, except it's multiplied by y and x respectively. And then the center of mass is going to be given by x bar and y bar, where x bar is going to be my divided by the mass, and y bar is going to be mx divided by the mass. So let's find all that stuff out. First, we want to identify the region D or R, in this case R, and it's a triangular lamina that involves this. So that will essentially get us set up to find the limits of integration for our double integral. All right, so we have those 3 points are given here. Let me take some of the stuff out. The 3 points are given here. We have 0, 0, 0, 3, and 3, 0. So we can take a look at that region as the region being bounded by the x-axis, the y-axis, and a line passing through these 2 points, 0, 3, and 3, 0. I think if we find the line through whatever means necessary, we will get the line y is equal to 3 minus x. And then this is the region we want to describe. So we have the line 3 minus x. Let's label that. What we would be interested in doing is drawing a line either parallel to the x-axis or the y-axis that goes through this region. I think I will draw a line parallel to the y-axis to imagine taking this region as a type 1 region. And so depending on where we are, it looks like we're going to be entering through the region. Let me see. I think I want this point. We're going to be entering through the region at this equation y is equal to 0. And then we're going to be exiting at this function y is equal to 3 minus x. So those will end up being our limits. And regardless of where you are in your region, it's always going to be the same entry and same exit points. And so this is the region that we want to describe. It turns out that in Desmos, if you were to describe this region as a set of inequalities for y going from 0 to 3 minus x, and then we set a set of inequalities for x going from 0 to 3, we would actually be able to describe the region that we're intending on describing. And so this region here can be described with our integral limits as y going from 0 to 3 minus x, and our x going from 0 to 3 constants. Okay, so I think with that, we should be able to set up our integral. Just take a quick shot of this to have in our notes. Maybe even take a shot of our actual graph. Then we can set up our double integral. So our double integral, let's see. In general, we're looking for the mass here, and that's according to the formula, the double integral over your region R of your rho, which is the square root of x times y. And then in this case, it's just going to be dA in general. And then now we're going to see how we're going to write that as an iterated integral. So this outer integral will be the outer limits going from 0 to 3. And then the inner integral will have limits going from 0 to 3 minus x. We will have our same function that we're looking at. And then in this case, we're integrating this with respect to y first. And then after that, we integrate this with respect to x. All right. So it turns out that this integral is not very easy to do by hand, and you are encouraged to examine other ways to compute this integral. And so we will do it like that. You can use Wolfram or whatever else might be useful for you. Let's go set up the math input. And then we have our outer integral going from 0 to 3, and our inner integral is another integral from 0 to 3 minus x. And then our function is a square root of x times y. And again, we're going to integrate with respect to y first and then x. All right, so we'll do that computation and we'll see that it will give us, strangely enough, something with a pi in it. So 9 pi over 8. All right, so let's keep that as a result because this is going to be our mass. Let's put it here. Okay, so now we have the solution for our mass. Actually, let's type it in here as well. So this is equal to 9 pi over 8. All right, so that's checkpoint 5.33. Let's move on to checkpoint 534, where they ask us to find the moments. So the moments will essentially be almost the same thing, except you see the difference here is that for mx, we multiply it by y. For my, we multiply the density by x. So we can literally, well, at least for me, I'll copy and paste. Now this is not needed here. So we will say this is our capital M. Let's do y first, or let's do x first. M sub x. And then the m sub x will be multiplied by y. And then so we will take this same integral, it's already set up, and then we'll multiply this by y. So let's go ahead and have Wolfram do the work for us, where we'll multiply this by y, and then it'll give us our mx value. Take a little bit of the minute here. It looks like it's 81 pi over 64. So let's mark it here. That's equal to 81 pi over 64. Let's throw it off to the side here as well. All right. Let's find my. Again, everything is all set up for us. My, except we're going to change our integrand to be x times the density. That's x times the density. And then we'll have it punch out our result. So let's change this y to an x. And then see what we get. Oh, we get the same thing. Interesting. Also get 81 pi over 64. So maybe I shouldn't have erased our result here. But that's our result. Okay. So that finishes off our checkpoint 5.34. And then our last one is to find the center of mass. And the center of mass is using the previous two checkpoints where we find X bar and Y bar. So let's see, X bar is equal to M sub Y divided by M. And what is M sub Y? It's 81 over 64. Divided by 9.8. And I see the 9s cancel and one of the 8s cancel. So I think that's just 9.8. The pi's cancel also. So I think that's just 9.8. It looks like Y bar is going to be similar. Oops. Is going to be similar. Not similar, it'll be exactly the same. Let's see. I just want to copy this and label this as Y bar. So Y bar is M sub X this time, which happens to be also 81 pi over 64. And then so you get 9.8 as well. So looking back in our Desmos, in our graph, in 2D, in the domain, if we get the 0.9 over 8, I'm sorry, I think I said 9.8. It's clearly not that. It's 9 over 8. This point over here would be the point where if you had this plate, you would be able to balance this plate at this point given certain densities. So maybe it's heavier on the edges out here and lighter on this end. So that's why this is pushed over to closer to the 3, that y equals 3 minus x edge. And so that's why it's over there, but it's symmetric about the line y is equal to x. So it looks like it's right on that diagonal. In any case, we have our solutions for our center of mass. So let's be really specific. Center of mass is going to be given by the point 9 over 8, comma 9 over 8. Oops. Let's try that again. 9 over 8, comma 9 over 8. All right. Yeah, and why not include this drawing as well? Oh, let's identify it. There we go. All right. That's it. So we got 3 checkpoints figured out here, and we have all the results listed. And this is the answer that's found in the back of the book, by the way. All right. I hope that's good. Good luck.